Lens Aberrations 1 by M.K. Srivastava, Department of Physics, Indian Institute of Technology, Roorkee, Uttarakhand. In this and the next lecture, we shall study and analyze the defects in the image formation by lenses, the lens aberrations. So, in studying the formation of images by refracting surfaces and lenses, we make the assumption that the object point does not lie far away from the axis of the optical system, and that the rays taking part in image formation are essentially those which make small angles with the axis of the system. Sometimes we may not say this predominantly, but this is an implied assumption all the time. To the extent these assumptions are true, the images of the objects will be perfect. All rays emanating from a single object point will converge to a single image point, and the magnification of the system will be a constant, independent of the particular ray under consideration. In real systems, however, non-paraxial rays also take part. These are the marginal rays, or rays making a larger angle with the axis. They also take part, sometimes even dominate in the image formation. The result is that the actual images are not ideal images. This deviation is essentially due to sin theta not being equal to theta for non-paraxial rays where theta is not small. In the next approximation, the so called third order theory, sin theta is replaced by theta minus theta cube divided by factorial 3. In this theory, the aberration of any ray, the deviation from the prescribed path for the paraxial rays, is expressed in terms of S1, S2, S3, S4, S5, called the Seidel sums. If a lens were to be free of all defects in its ability to form images, all 5 of these sums would have to be equal to 0. Now, no optical system can be made to satisfy all these conditions at once. Therefore, one considers each sum separately, and its vanishing corresponds to the absence of certain aberration. Thus, if for a given axial point the Seidel sum S1 is 0, there is no spherical aberration at the corresponding image point. If S2 is equal to 0, the system will be free of comma. The sums S3 equal to 0 and S4 equal to 0 correspond to no astigmatism and no curvature of the field respectively. If S5 could be made to vanish, there would be no distortion of the image. You see, these aberrations together are called monochromatic aberrations, as they exist for any specified color for any refractive index. In addition, if the light used for image formation is polychromatic, like white light, which is used in almost all optical instruments, then in general the images will be colored. This is due to the dependence of the refractive index of the material of the lens on wavelength of the light used. Different wavelength components in the light proceed along different directions after refraction and naturally form images at different points. This is called chromatic aberration. Let us study chromatic aberration first. Consider a parallel beam of white light incident on a thin lens. The incident beam is a white light. After refraction, the colors they appear. Since the refractive index of all the transparent media varies with color and blue light gets refracted more than the red light, a single lens forms not one image of an object, but a series of images, one for each color of the light present in the beam. You see, the prismatic action of the lens, which increases towards its edges, is such as to bring the violet light to a focus nearest to the lens. As a consequence of the variation of the focal length of a lens with color, the lateral magnification must vary as well. So, that is an additional aberration coming up. You see, let us see this situation here. The figure shows red and violet image heights of an off axis point O. You see, consider the point M which is on the axis. The image is violet image and the red image, they are not at the same point. Similarly, if you consider an off axis point, here again the corresponding q prime r and q prime v, they are not at the same point, leading to a chromatic aberration in the lateral side. So, lateral and longitudinal, both of these features will be there. The horizontal distance between the axial images is called axial or longitudinal chromatic aberration, as we have seen in the last picture, while the vertical differences in height called the lateral chromatic aberration. Because these aberrations are often comparable in magnitude with the serial aberrations, corrections for both lateral and longitudinal color is of considerable importance. Now, the expression for the longitudinal chromatic aberration can be obtained from the lens formula. You see, the lens formula is 1 upon f is equal to n minus 1 multiplied by 1 upon r 1 minus 1 upon r 2. You see, we are assuming the same medium on both sides of the lens. If we differentiate it, we get minus delta f upon f square, delta n times this factor 1 upon r 1 minus 1 upon r 2. We substitute its value. So, this becomes equal to delta n upon n minus 1 times 1 upon f. So, delta f is equal to minus f times delta n upon n minus 1. So, this means the difference between the focal lengths for red and the blue, f r minus f b, is equal to f times delta n, means refractive index for blue minus refractive index for red, divided by n minus 1. So, now let us look at possible methods to make a achromatic combination, at least to minimize chromatic aberration or to try to eliminate it. While there are several general methods for correcting chromatic aberration, the method employing a combination of two thin lenses made of different materials, say crown glass and flint glass, one converging lens, the other diverging lens, and placed in contact with each other, is the commonest, the convex lens and a concave lens. The method will be, if this combination NB minus NR upon N minus 1 for the material of one lens, and similarly omega prime the corresponding for the material of the other lens, you see, these quantities are called dispersive powers. So, suppose we have two lenses of crown and flint glasses of dispersive powers omega and omega prime, and f prime are respectively the focal lengths of the converging and the diverging lenses. Then the condition for achromatism is given by this. This actually follows from the last relation we obtained, because for the longitudinal difference between the two foci for blue and red, that is really given by omega by f. So, omega by f for one is compensated by omega by f by the other. The focal length of the combination naturally will be given by this relationship. Now, although the lens in our above example would appear to have been corrected for longitudinal chromatic aberration, it has actually been corrected for lateral chromatic aberration as well. You see, the equal focal lengths for different colors will produce equal magnification, but the different colored images along the axis will coincide only if the principal points also coincide. Focal length becoming equal is not enough. The focal point should also coincide, and that will be the situation if the principal points also coincide. But practically speaking, the principal points of a thin lens are so close together that both types of chromatic aberrations can be assumed to have been corrected by the above arrangement, in which you have two thin lenses, one concave, other convex, of different materials, satisfying that relationship of omega by f plus omega prime by f prime equal to 0. In a thick lens, however, the longitudinal aberration is absent if the colors corrected for come together at the same axial image point, like this for both the colors, red and blue. But see here, as the principal point, this is the thick lens, as the principal point for the blue and red do not coincide, the focal lengths are not equal, and the magnification is different for different colors. Consequently, the images formed in different colors will have different sizes, and the system will suffer from lateral chromatic aberration. The chromatic aberration can also be removed by taking a combination of two converging lenses of the same material separated by a distance t equal to the mean of their focal lengths. The focal length of the combination is given by, we have obtained this relation earlier, 1 upon capital F is equal to 1 upon f plus 1 upon f prime minus t upon f prime, and the thickness is kept as mean value f plus f prime by 2. This arrangement has the same focal length for all colors near those for which f and f prime are calculated. For visual instruments, this color is chosen to be at the peak of their visual brightness. Such spaced doublets are used as oculars in many optical instruments, because the lateral chromatic aberration is highly corrected through the constancy of the focal length. The longitudinal aberration, however, is relatively large due to wide differences in the principal points and therefore wide differences between the focal points. But because the focal lengths are equal, the image sizes are equal, lateral chromatic aberration has been taken care of. An illustration of a system that has no longitudinal chromatic aberration is shown here. It is a combination of a convex lens and a concave lens. You have got the red and blue images at the same position. Remember here, the focal lengths are not same, because the principal points are not at the are not at the same point for blue and red. So, here the images are formed at the same point, but they are of different size. Now, we come to the monochromatic aberrations, like a spherical aberration. Consider a beam of light parallel to the axis incident on a thin lens. The light rays, after passing the lens, they bend towards the axis and cross it at some point. Now, if one does not restrict to the paraxial region, then in general rays which are incident at different heights on the lens hit the axis at different points. For example, for a convex lens, the marginal rays which are incident near the periphery of the lens, they focus at a point closer then the focal point of paraxial rays. Fp is the focal point of paraxial rays, Fm is the focal point of the marginal rays. This figure also shows the difference between the longitudinal spherical and lateral spherical aberration. Similarly, for a concave lens, rays which are incident farther from the axis, they appear to be emerging from a point which is nearer to the lens. Fm is nearer to the lens compared to Fp, which is the focal point for the paraxial rays. Now, the point Fp at which the paraxial rays strike the axis is called the paraxial focus, and the point Fm at which the rays near the periphery strike is called the marginal focus. The distance between the two is a measure of longitudinal spherical aberration in the lens. Similarly, the distance between the paraxial image point and the point at which the marginal rays strike the paraxial image plane, that is called the lateral spherical aberration. Now, spherical aberration can be minimized as appears naturally by using stops, which reduce the effective aperture. The stop use can be such as to permit either the axial rays of light or the marginal rays of light, not both. But however, as the amount of light passing through the lens gets reduced, correspondingly the image appears less bright. Now, let us label the lens by a number. This is called the shape factor, R1 minus R2 upon R1 plus R2. A series of positive lenses of the same diameter, same aperture, same size and same paraxial focal length. So, we are making a comparison of lenses of different shape factors, different combinations of R1 and R2 of all these lenses of the same size and of the same paraxial focal length, but of different shapes. We consider these. Each lens is labeled by some value of q that we show now in the next figure. The alteration of shape is known as the bending of the lens. Let us consider 1, 2, 3, 4 several lenses, different shape factors are given here. For a biconvex lens, that is number 4, shape factor is 0. In the bottom figure, on the vertical axis we have got the height of the ray. 0 means along the axis, and from 0.5 going up to 2.5, that is the height of the ray, and on the horizontal thing it shows how much the difference is there, how much is the magnitude of the longitudinal aberration, difference between Fm and Fp. And we find here that for the shape lens of a shape factor of plus 0.5, this variation is minimum. So, this shape corresponds to a shape which will lead to a minimum spherical aberration. We find that by choosing the proper radii for the two surfaces of a lens, the spherical aberration can be reduced to a minimum, but naturally it cannot be made to vanish. You see this, let us see that basically why the spherical aberration is coming up, and can we do something better than this? The spherical aberration is the result of marginal rays undergoing a large deviation. So, we should expect the spherical aberration to be minimum when the angle of deviation is minimum. As happens, this would occur as in the case of a prism. When the deviations suffered at each of the refracting surfaces are exactly equal. Such an equal division of refraction will yield the smallest spherical aberration. And see, for the shape factor, remember we have seen for the shape factor of 0.5, This is again we are showing the same thing. On the vertical axis is the spherical aberration and the shape factor on the horizontal axis at the point close to 0.5, that is the minimum of this curve. The reason basically is that the total deviation caused by the lens is almost equally shared by the two surfaces. Now, although the spherical aberration cannot be entirely eliminated for a single spherical lens, it is possible to do so for a combination of two or more lenses of opposite sign. We want to cancel out the effect. The amount of spherical aberration introduced by one lens of such a combination must be equal and opposite to that introduced by the other. If, for example, the doublet is to have a positive power and no spherical aberration, the positive lens should have a greater power. Positive lens means a converging lens, and its shape should be at or near that for a minimum spherical aberration, while the negative lens, which is the concave lens, should have a smaller power and its shape should not be near that for the minimum. Neutralization of spherical aberration by such an arrangement is possible, because the spherical aberration varies roughly as the cube of the focal length. In a cemented lens of two elements, the two interfaces should have the same radii naturally. The other two may then be varied and used to correct for spherical aberration. So, thus with 4 radii to manipulate, 2 for each lens, other aberrations like chromatic aberration can be reduced at the same time. Now, using this criteria of equal deviation for a combination of two thin lenses, one finds that the spherical aberration is minimum when their separation is equal to the difference in their focal lengths. Have this combination. The curved surface of the plano-convex lenses faces the incident light. This is to divide the total deviation over the surfaces. So, in this arrangement the total deviation is equally shared by the two lenses, and with this we have come to the end of this lecture. We have studied chromatic aberration and spherical aberration. In the next one we shall take up other monochromatic aberrations, and these are coma, astigmatism, curvature of the field and distortion. Thank you.